So good morning, good afternoon, or good evening, everybody, depending on your time zone. I'm very happy to see many of you participating to these webinars, and today we have the pleasure to have Professor Lucia Capra from the Istituto di Geoscienza UNAM. She will talk about erosion and degradation on active volcanoes 2015-2025 lahars activity at Volcán de Colima. As always, you can drop down questions during the presentation, and I will read all the questions at the end to Lucia so she can answer us at the end of the presentation. Please, Lucia, thanks a lot.
Okay, thanks for the invitation. Hi to everybody. Today I would like to show you, this is quite an upgrade of the presentation that I gave last year at YAFSE about the erosion aggradation processes at Volcán de Colima, which is one of the most active volcanoes in Mexico. In collaboration with my colleagues from the University of Colima and Morelia and Senapred de Civil Protection here in Mexico. So, aspetta, come si fa? Okay. So in my talk, I will give you an introduction, very short introduction about the sediment source of Volcán de Colima and the characteristic of the lahars, which are the main factor in promoting sediment remotion. And to better analyze the erosional and depositional process during the last 10 years, I will show you some evidence of the morphological impact of the eruption of July 2015. Then I will show you the monitoring system that we have since 2010 to mostly focus to monitor lahars, to set up an early warning system, but we are using also the data to analyze the erosional processes, and also all the drone survey that we did since the eruption, which have been used to analyze the morphological changes. And finally, the results, the relation between the observed data and the erosion processes. Okay. So where the sediment came from, Colima volcano, mostly from the eruptions. During the last century, the volcano experimented one Plinian eruption in 1913, and several episodes of dome collapse generating block and edge flows. Here is a picture of, can you see my mouse or not? My pointer? Maybe not.
Yes, we can see it.
Okay, this is a picture of this summit dome just before, 3 days before the collapse that generated a pyroclastic flow. And you can see here a view of the Monte Grande ravine. The data that I will show you are focused only on the Monte Grande ravine. And you can see that the valley was completely filled by block and edge flow. During the eruption lasted the 10 and 11 July. Approximately 8 million of cubic meter of sediment were emplaced along the ravine. Then we have a second process, which corresponds to seismogenic landslides. This is a picture of the event that occurred in 2024 due to a 4.8 earthquake. You can see a lot of superficial landslides, soil slips, and along the channel, the Authentique ravine. We estimated approximately 1 million of cubic meter of material associated to this process. And why? The volcano is surrounded by a very strong tectonic framework with active faults. So the star indicate the epicenter of these events, and this is the Authentique ravine. And finally, each year along the valley, the ravine, which is bounded by very steep walls, during the dry season, we have a lot of small accumulation of material from vertical detachment of the material from the valley wall. You can see that some of them, the largest, can completely block the river. And the first lahars during the rain season are sometimes blocked by this obstruction, and they progressively start to erode again the material up to reopen completely the channel. And this is a movie, an example of the lahars. This is Monte Grande Ravine. The movie is about a lahars recorded in 2018, was the largest event. So this is the morphology of the channel 3 years after the eruption. You can see the lahars mostly usually are confined into the main channel. And particularly this lahar was the only one able to overtop the channel. You will see the last pools. Generally, the last pools are the largest. These lahars lasted more than 1 hour. And I will see, this is the last pools. They were, okay. And for scale, the white line is 10 meters. And the channel at that time was 3 meters deep. And note that it's not raining. So this is one of our main problems, to correlate rainfall, lahars, erosion, deposition, because rainfall can be very erratic. So we have a rain station 2 kilometers up from this point, and the record, it wasn't able to record any rainfall for this event, which was the largest one for the season. And this movie, just to introduce you the argument, you will see the morphological change during the 2019 lahar season. So this is one image for each year of the years. And you can see that at the beginning of the rain season, usually we observe small lahars that can be mostly depositional. Because they are trigger a very the lowest rainfall event that accumulated around 10 millimeters, 15 millimeters. But toward the end of the rainfall season, we have the largest rainfall events associated to tropical rainfall. You will see that most of the lahars are erosive. They clean the channel and producing an increase in width and in depth. You will see now one of the last that was very large and completely eroded. Also note the difference in the channel morphology before the video that you saw before at this one in 2019. I anticipate you that the season, the 2018 and 2019 seasons were the largest one in lahars activity. So this was the morphology before. Now we move to the effect of the eruption on the channel. This was the morphology of the ravine prior to the eruption. You can see here the monitoring station that was installed since 2010 to monitor lahars. This is an image few hours before the dome collapse, and let me show you this. Okay. And this is the movie of the pyroclastic flow that was captured by the camera. So you can see how the block and edge flow valley confined. This is the first pulse that arrived. Then we detected several pulses. So at this point, the station was already destroyed. And this is the ravine after the eruption. The station that captured the video was installed at least here, this point somewhere, and was buried by at least 8 meters of PDCs. So you can see that after the eruption, the topographic relief was quite smooth. You don't see a main channel, just a depression in the middle sector of the channel. And other morphological change, we move the picture that I show you. The station was here, 6 kilometers away from the crater. Now we move close to the cone. This is a picture before the eruption. So still a quite well-defined ravine and all filled by lahars deposits. And this is approximately the same position. You will see no more vegetation. Everything was destroyed and completely filled by pyroclastic flow. This picture, we went October 6th, now August 6th, 2 weeks after the eruption. You will see that it was already raining, so this few lahars already originated from the eruption, hot lahars in that case. And this is the distal portion of the ravine. We are here. This was the main depositional area for lahars. You will see that the ravine opened on a distal fan. Here, aerial view, you see the main channel where lahars were draining and depositing material on both sides. And this was is a picture taken the 11th July, the day after the main pulse. You can see that was already completely covered by PDC. This channel was here, approximately. You will see here there is a high tension system crossing the area. The deposit, just 2 weeks after the eruption, all the area was covered by very fine ash from the co-inubiity cloud of the PDCs and a fine grain deposit. This is a portion, is a section on an overbank. In a main channel, the deposit was massive with blocks, centimetric blocks, embedded in a very fine matrix, very loose material, and close to the source, the texture were quite similar, but with an increase in block sizes. And it wasn't just one unit, but several units. And you can see in this picture taken in 2016, a sequence of several block and ash flow deposits layers from both eruptions. The eruption occurred 10 and 11 July. So let's move to the monitoring system. So this is the Monte Grande ravine. The star reflects the position of the monitoring station. We have several instruments because we look to set up an early warning system for lahars. So an automatic detection of it. So we use video camera, seismic sensor, infrasounds, and rain station. One here, and the other one that I told you before is here, very close to the edifice. And we also have other monitoring stations in all the main ravine, as La Lumbre, Sarco, and Arena. All the data are transmitted in real time to the Colima University. And then we receive here Querétaro. We are 7 hours away from the volcano. And about the drone survey, we start just after the eruption. This is 8 August 2015 with LiDAR, terrestrial LiDAR. We did a survey in the distal fan and in the middle where we have the monitoring station. Then we did the same survey on November of the same year. Just so we include here a rainfall season. And then we did with drone other survey in 2016, 17, 18, 19, then the pandemic, 2021, 22, different instrument, different people taking the flight, different initial condition. I will show you the problem that we have now. And we also have a Pleiad image in 2017 and a spot image in 2016, 17. And last year, we finally get a nice drone with a LiDAR camera. So we were able to survey all the ravine, all along the ravine, from this point up to here, at least. And we just did a new fly in April. So we used the new fly, the LiDAR fly, to try to re-geoference all the old drone survey, because we have a main problem. If you would like to quantify the erosional rate, we have to be able to overlap all the drone with very small errors. So we reprocess all the drones. I reprocess all the drones fly to try to get the lowest error as possible. So, how lahars start at Colima? The main process is, I don't know, is from, this is a movie that we took directly in the ravine. This is La Lumbre ravine. You can see that no clear water is running. So the main erosional process occurred, this point is 5 kilometers away from the main cone, up valley. So the water runoff start to erode the sediment along the riverbed, and a progressive increase in sediment will promote a change from stream flow, hyperconcentrated flow, and debris flows. So depending, so the energy of this process will depend about where it starts to rain, so the slope of the channel at the site where rainfall is accumulating, the grain size of the riverbed, and the density of the flow, because as the flow increases sediment concentration, we'll have more capacity to erode the material along the channel. Okay. And another important factor is that in general, the magnitude of the lahars depend on the total accumulated rainfall, so the volume of the water available, because at volcano you always have a lot of sediments to erode. So all depend on how much water is running down the valley, and obviously the geometry of the watershed. La Lumbre ravine as the largest one. So usually we observe the largest lahars at the volcano along the ravine. And in contrast to the Monte Grande ravine, which has a very small, smallest watershed. But the main difference is also that we can see lahars at the Monte Grande ravine even with very small rainfall, because it has a very quick response to water runoff. Instead of La Lumbre, to have lahars, we need very strong rainfall event. So we have two different behavior in the same volcano in two different ravines. This is quite important for hazard assessment, for example. And this is an example of how we use the seismic data. This is an example from the 2018 lahar season. You can see here the topographic relief of the ravine. These are the monitoring site here. Again, this is the same point that I showed you before. And based on the images, we were able to qualitatively define the flow depth. And then we correlate the observed flow depth with the seismic amplitude. And we observe a positive correlation. So as seismic amplitude increase, flow depth increase. So this could be useful to define the magnitude of the event. But then we move to try to correlate the seismic signal also with the sediment concentration using the frequency content. So debris flow are typically characterized by lowest frequency content respect to hyperconcentrated and stream flow. So why we are interested to do this? Not only for the hazard assessment, but also to better correlate erosional and depositional processes, because as we saw based on field data, debris flow, deep debris flow are much more able to erode the channel with respect to hyperconcentrated stream flow. So it could be an important factor to use to correlate the change in morphology of the ravine. This is a picture of the lahars deposits. Debris flow with very large block or more diluted. You can see here a nice relationship between the deposit from the 2015 PDC and the lahar on top. And it's very common to observe along the channel after an event several steps reaching blocks, which forming as from the lahar front, which usually reach or large blocks that stuck together and then are not able to move over. So the subsequent surge flow on top of this large step. This is also a process that promotes surge formation during a lahar. So let's look at some results. Here you can see the catalog of lahar events since 2015. 15 events just after the eruption. And this year is particularly important because the Hurricane Patricia was of category 5, hit directly the volcano. So during 3 days, we recorded around 300 millimeters of accumulated rainfall. And along the La Lumbre ravine that I showed you before on the western, we recorded one of the largest lahars that we saw at the volcano since we installed the monitoring system. And lahars were also generated along the Monte Grande ravine. So it was the first large event after the eruption. Then if you can see along 10 years, we recorded almost 200 lahars. The 2019 season were the largest, also because recorded the largest amount of rainfall. And you can see that lahars are usually associated with the largest amount of accumulated rainfall. During this, in 2019, we had 121, in 2015, 115, and with very high intensity. Then we don't have data of rain from 2020, 2023, and you can see also that after the pandemic, we have several problems in data transmission and technical issue. But now, since last year, we were able to put everything in working, so we are now able to record perfectly lahars and rainfall. This is just to show you how rainfall can be correlated with lahars. This is an analysis just for the 2018 season, 2019. In blue are all rainfall events. Rainfall events are classified when based on more than 60 minutes without rainfall. And the red symbol is related to the rainfall that triggered lahar. So statistically, during 2018-19, the rainfall that triggered lahars in average accumulated 17 up to 20 millimeters. The maximum peak intensity calculated in a 10 minutes window is from 100 to 120, and the duration is not significant. Duration of the rainfall is not a significant factor in discriminating. But again, at Colima, it's not easy to try to fix a threshold, rainfall threshold that above which lahars are triggered because of the erratic distribution of rainfall. So now I will show you some results about the depositional and erosion processes. In the proximal, we start from the proximal area. We don't have a drone survey. We only have a few images from the Pleiades, Google, and fieldwork. So here an image of Google, I think, in 2015. You can see that you can identify a real channel. And just 1 year after, you can see that an important thickness of deposits is already eroded. Here is a picture taken in 2016, the same one that I showed you before. You can see that already at least 10 meters of PDC were already exposed. So a strong erosion of the sediment occurred in just 1 year. In the proximal area here, the slope is about between 15 and 20 degrees. And 4 years after, this point is like a nick point, migrated 200 meters up to here. And at this point, in 2020, the bedloaf of the ravine is exposing again. So all the PDC were already eroded from the middle of the channel, not from other banks, but in the middle. So a strong, we cannot quantify now, but it was really, we observe a very strong erosion of the material. This is in the middle ridge where we have the station. So these are an example of section between 2016 and 2019. And this is just 600 meters long, and you will see very different pattern in a very short distances. Here you can see how at the beginning is very small channel are forming. At the beginning, where the topography was really smooth, you don't see a main channel forming. The water runoff is dispersing on top of a smooth surface. It's not able to concentrate. And then when a small channel starts to form, the water is able to concentrate and erode a main channel. Here, the first lahars were depositing. You can see here is like 2 meters thick deposit that forced to migrate the channel toward the western portion of the channel. And so mostly a migration. And here we can see a migration. And now remember, this is the section of the same video of the lahar that you saw at the beginning. The channel migrate and became deeper. Nowadays, the channel is 5 meters deep. In the distal portion, we have a problem. So we did a survey in 2015, two surveys in 2015. This is 2015, 2017, 19. You see that a small channel is forming again. I was prior to the eruption. But now all the material accumulated in the fan is used for construction. So we have we cannot use the data anymore because it's completely the topography is changed by all the activity to extract the material. I don't know how they get the permits to do this, but I don't know. It's Mexico. So here are some preliminary results that we are trying to obtain to really have a quantitative estimation of the erosions. This is the surface obtained by the terrestrial LiDAR in 2015 in August and in November. You see here a very smooth surface, as I show you in the picture, in a panoramic view. And here, 3 months later, you can see a few channels. So by overlapping the two surfaces, we obtain this, where you can see in purple deposition and in brown erosion. You can see a very strong deposition in this portion of the ravine before we start with a lot of bend in the river. And here a section shows that before and after there is at least 4 meter thick lahar deposit that was originated by the lahars from the Patricia hurricane, and just a small channel in this side and in the other side. And here, close to the monitoring station, same process. Mostly the positional, and then usually the tail, a very dilute tail, are able to remove part of the deposits, leaving a small channel covered with a very fine material. So apparently during the 2015 lahar season, due to the smooth morphology of the channel, lahars at this section, just at this section, not at the proximal one, were mostly accumulating sediments. We don't have images. Yes, this is an image of the lahar associated to Patricia hurricane. The material was still hot. This was in October. So there is a lot of steam because of the hot temperature of the lahars. But you can probably appreciate how the lahar remain channel here. So apparently it was not a very large lahars as we observed the same year in the other ravine. And this is a resume of what we are doing with all the drone survey. This cost me blood because I have to reprocess all the DIM with the new LiDAR survey. But the main point here is to show you that at the beginning, just after the eruption, at this section, the lahars were mostly in a depositional range. You see again, the same color, the purple is erosion. This is the same that I just showed you. 2016, it became more clear, a channel in this portion. Then in 2017, the dams refer to the end of the season. So at the end of 2017, you have here again a channel. And then the 2018 and 19 were the most active season in lahars. And a very well-defined channel is already formed. And this is, 10 years of comparison. So after 10 years, you can see that we have a very nice channel along the ravine. And this is a resume of the data of the number that we get. So in light blue is rainfall, accumulated rainfall. In data are now quite confident for 2015, 16, 17, 19. I have problem with the other season because of the overlap of the DIM. So you will see, and the red line is the number of lahars. As I told you before, the 2019 was the largest season in lahars formation. And in blue is the erosion rate, and in orange, the depositional rate. So for 2015, we estimate 3 meters cubic per square meter per year of deposition and 0.39 of erosion. And the trend is inverting as we move along the years, up to the 2019, where erosion was no longer observed along the channel, the deposition, sorry, but only erosion. A balance between 2016 and 2025 indicate a total erosion rate just in the middle section of 6 cubic meter per square meter with an error of 1 meter. See, each year I think that we accumulated like 10 centimeter of cubic meter of error. So I know this is very bad, but it was it's just a schematic way of how we interpret the change in depositional and erosional processes. At the beginning, again, the surface was very smooth. So water now was not concentrating in a main channel to promote erosion. Up to the first channel form, and as now we have a main channel where all the material is all the water is concentrated and lahars are able to erode. The channel, the ravine, is made by all the debris avalanche deposits. This is Tonila deposit as an age of 15,000 years. Then we have the pyroclastic flow from the 1913 Plinian eruption. And before the 2015 eruption, several terraces of lahars. It's important to note that the 2015 eruption was the largest observed since the Plinian eruption. Usually PDC were reached from dome collapse, were extending up to 5-6 kilometers from the source. And so the 2015 event was the first one with PDC reaching up to 10 kilometers away from the source. So we expect that in near future, the channel will increase its depth, and we are now processing the data from 2025, where we really have a very nice LiDAR survey, rainfall data, and lahars. So we need to better understand now, which will be the evolution, if the erosion will, if the ravine is now much more stable, so if erosion will be suppressed or and the main problem here is that we don't have data in the distal fan. So we have, but we cannot quantify where all the material eroded because the proximal area is dominated by erosion, or if the channel, all the material, where will end. Something that I didn't tell you is that from the monitoring here, this is this monitoring site. After this curvilinear path of the ravine became much more larger. So from this point up to here, we have been observing along the last 20 years is mostly depositional. So here mostly erosional, became still erosional up to here approximately, and then became depositional. Of these, curvilinear morphology is slowing down the lahars. So here we were able to calculate velocity of lahars around 4, 5, at least up to 8 meters per second. And here very slow lahars. So the movie that I show you was accelerated, but usually very slow because also of the block ridge fronts. See, but here is mostly the positional. So I think that the area that we are analyzing is the most interesting to better discriminate between erosion and the positional regime. And so it's a work in process. We are now trying to get data of the distal reach because we have some data since 2015, but we have to try to analyze to get some data. And as I told you before, we have now very recent nice data. But at least we can see that from the data that I present you, that the erosion and the positional processes are very different, can be very different just after an eruption. So in our case, the most active season in lahar formation in erosive processes occurred 3 years after the eruption. The same year of the eruption, even we have very strong rainfall event like the Hurricane Patricia. Yes, the proximal area was deeply eroded, but down the channel, because of the smooth morphology, the lahars were mostly depositional. And as in 2018, the channel was already formed, the behavior changed. So I think this is, for us, assessment is quite important, to better understand after an eruption, which will be the behavior of lahar formation and sediment transport. And finally, this is for me, because when we start to study everything just after the eruption, we didn't plan too much all the activities. So now I'm fighting with all the data that were taken like in different ways. So I suggest you to plan very well your strategy since the beginning. And that's all. Many thanks.
Okay,
we have too much data. Yes.
So if someone wants to help Lucia and go to Mexico, please just write her directly. Okay, so you're more than welcome to go to Mexico if you want. So thanks a lot, Lucia. It was very, very interesting. Let's see if someone has a question. You can write down the question as I told you before. And let's see, let's wait a little bit. Yeah, I have just a curiosity. Have you do you know, because you told us that you have some data probably from the distal part, but do you know how long those kind of lahar sedimentation can impact the fluvial system? I mean, far away from the volcano?
Before the eruption, we have been studying lahar's activity for more than 10 years. And even when so it was a very nice, stable channel. And since you have a lot of material in the source, the magnitude, the frequency of lahars were mostly regulated by the characteristic of the rainfall. So in 2011, we had a very large event correlated with another hurricane. So, for example, after the 2004 and 2005 eruptive activity, we observed an increase on the magnitude of the lahars the first 2 years, and then it decreased. So, for example, I think that this is the volcano now, the volcano is dead. So if you don't have more eruptive activity in the next 10 years, the proximal areas is quite depleted now of material. Is lava flows outcropping now in the riverbed. So I think that lahars will decrease in sediment concentration. We will have very large rainfall event, but it will decrease up to the next dome growth. But now the volcano is. So it's now very nice to try to understand what you are saying, because if you can really have nice topography relief data, we can see in the next year how will change the sediment erosional processes without an volcanic input.
Yeah, that's right. Okay. Oh, we have 3 questions. Thanks a lot for your answer. The first question by John Measure, or probably was by Caroline Emmett, because I saw that Carly was writing, but then at the end. So let's start with John one. When you compare timing of flows to seismic data, how good is the timing of how well sensed the seismic data?
GPS system. So the oldest seismic sensor at GPS, and the camera as a GPS server. So we are able to match the seismic data with the image. With the rainfall, we have a problem because we use, probably you can see our rain station here is broken. And we don't have a time, an exact time for the rainfall. But this is not, the main problem is the rainfall are so erratic that we cannot really correlate it. But yes, we have a very nice match between the time of the seismic record and the images. This is yeah. I think that is, part of the seismic data used are the same that University of Colima used for the seismic monitoring of the volcano. So it's very quite rigorous data.
Okay, thank you. The second question by Caroline Emmett. Could you please elaborate a little bit your last comment on the resolution and scale issue, what you labeled, at least for me, as an issue?
Of the DIM, of the topography? Okay.
Yeah, I suppose, yeah.
Yes, what I did, I took fixed point now from the 2025 LiDAR survey, from points that I was able to recognize in all the oldest surveys. So I used that reference point. I took like about 50 for each survey, and tried to recalibrate the oldest flies, the oldest data. So what I observed is that are you still seeing my presentation?
Yes. Yeah,
okay.
Yeah.
Okay. The largest error that sometimes can be up to 1 meter, the error is in altitude, is in the extreme portion of the survey. And here and here. No, here no, because this is a different data. Here and here. So I'm not considering for the sediment balance analysis from the extreme portion of the channel, just in the middle. And here in the middle, I get error between 10 and 20 centimeters between 1 year. Okay? So here for do this, I took we have a fly in August 2016 and December 2016. The December 2016 was used to was overlapped to the November 2017. The November 2017 was overlapped to, I have in DIM in 2018, I don't remember the, was October, and then November 2019. So for the calculation, for the estimation, I'm only using the central portion of the survey because I have a lot of error in the extreme sector. So if accumulating 10 centimeters is like 1 meter. I know that it's an issue, but I cannot do better. I hope to do better with the LiDAR drone survey, but at least it's an estimation, it's a quantification. We always used topographic profiles we published a work in 2018 with topographic profiles along the ravine, and now I think that we are moving to something more quantitative. I know it seems very large, too much, because it's too much, the value for you. 5 meters, 5 cubic meter, I don't know.
So,
but I know that there is a problem there.
So Caroli replied, thanks. I was suspecting this issue, but now you confirm me. You confirm it, thanks. Then we have a question by Pierre Bouiguet. Sorry if I'm not my pronunciation could be wrong. Thanks for your presentation. It was very nice. We observed those kind of processes also in Indonesia a lot. Did you observe overbanking processes able to create a new deposition erosion channel?
The main overbanking process that we were able to observe is here, but it's at the side of the main channel. So what we observed that before the channel became more deeper, the lahars were able to overflow. But now they are not more able to overflow the channel. So overbanking is preventing overflow. But here, if you consider this like an overbanking, at the beginning the channel formed here, and then the accumulation of the material forced the erosion to move toward the western portion of the channel. So of course that overbanking can force to migrate the channel to another side, increasing the hazard associated. Yes, of course. This is very narrow channel. It's very, very confined. All the lahars will be always restricted to this channel, but at small scale, we were able to observe. I think into other volcanoes like Fuego in Guatemala, obviously, and I saw some of these processes where after a big event, the channel moved toward the more populated area. So yes, I think that is it's important and it could be possible.
Okay, thanks a lot, Lucia, for your answer. Let's see, otherwise we can, let's see if someone want to, okay. John Measure said, in the tropical climate around Colima, it is common for rainstorms to be very localized rather than more widespread, yes. That is why you can have lahars occur without any apparent rainfall at monitoring sites, meaning the rainfall is concentrated at a higher elevation on the volcano. We saw this at Pinatubo in the 90s.
Yes, exactly. So rainfall are so erratic, and at the beginning, especially at the beginning of the rain season, you can see a very strong rainstorm, strong rainfall 1 kilometer away. We are in the channel, we see up to the mountain is raining, and after 2 hours a lahar is coming down. So yes, the movie that I showed you before in the 2018 ravine was sunny at the rainfall at the monitoring station. So usually in July, August, the rainfall behavior is more orographic. So a lot of rainfall accumulate up to the mountain. Then in September, October is the hurricane season. So you can have rainfall along 3 days. And at the beginning, because of the small rainfall intensity below 50 meter 50 millimeter, you don't have lahars. So all the rain is infiltrating. And just maybe the day before, you will start to see some events. But yes, it's very, very concentrated at higher elevation. But we have a rainfall station at higher elevation, but sometimes we don't have data of rainfall that can be correlated with the observed lahars. This is a problem, so we cannot set up a early warning system only with rainfall. We don't have too much rainfall data if station, no? We could have, we should install like 10 rainfall station all around the volcano. And we have radar data, but it's not very, sometimes it's work, but sometimes not. Radar data for rainfall, I mean. Like for the next 12 hours, and we can see how the rain is moving. And sometimes it corresponds with lahars event, but sometimes not.
So John is answering a difficult challenge. Very nice talk. Thanks. And then another question by Pierre, then we can close. When you say that you overlap your LiDAR data, which method do you use to co-registrate them before computing the difference and the volumes?
What do you co-register them before? As I told you, I think that, I don't know if the same, I used a fixed point. So there are very large blocks on the valley side that didn't move since 2015. So I identify all these blocks. I took the marker points from the LiDAR in 2025. So the coordinate X, Y, and Z, and I use it in, I use Agisoft, and I use those markers to rebuild again all the model. And then to define the error, I took the same markers and I calculate again the coordinate and the set value for the new obtained them and compare it with the original coordinate and altitude of the markers to obtain the error. And this is the error that I'm considering the average just for the middle section of the ravine, the average error. I get sometimes very nice correlation, like 1 centimeter of difference. And the worst one is about 10 centimeter. I don't know. And then I use ArcGIS Pro to overlap the DIM and manipulate to obtain volume and different thicknesses and so on.
The suggestion is maybe you could correct the ramp considering vertical shift and horizontal shift matrix. I had this problem using Pleiade data.
Maybe you could correct the ramp considering vertical shift. Yes. We already obtained a very nice DEM from Pleiade. He's a PhD student in Italy that just did a new DIM from Pleiades. When we try to correlate it with the LiDAR, it's still some, no, didn't work too much. But we are working on, so you can write to me if you have more suggestions, they will be welcome. Really, it's very tough work. It's not easy. It's easy to fly the drone, but not to elaborate the data.
Okay, so last question. Okay, thank you for your live presentation. I'm also curious about the correlation between the flow depth and the amplitude. Can you detect similar processes at other volcanoes?
Yes, Popocatépetl. We are working with Popocatépetl data. We have a lahar monitoring station, and we observe the same one. The main problem is that as the erosion process progressed and the channel became deeper, this means that the distance between the sensor and the lahars increase. So the signal attenuation increase. So you cannot correlate one, let's say you have the same lahars in 2018 and 2019, but the channel was 1 meter deeper. So the amplitude will change. See? So we see the same correlation, but not in absolute value. At Popo, the sensor is very close to the channel. Here is 40 meters away. In Popo is like 8 meters away from the channel. So we get very high amplitude that at Colima, we can get only with the largest lahars. So the trend, yes, but not in absolute values.
Okay, thank you. So Pierre was saying, okay, I have a full pipeline for you that, and then the last person that make questions say, I see, thank you for enhancing the information. Okay, thanks a lot, Lucia. I think that
thank you, Andrea.
You gave us a really interesting talk, and the audience also appreciated it. So for everybody, thanks a lot again for coming. Just remember you that we are still organizing the field trip on Argentina between the 19th and the 23rd of October. So you can go on our website and you can see all. You can have all the information there. We still have some free places. So please reach us if you want to come with us to Argentina. There is a really nice video also on the YouTube, so you can also see it on our social media. We will upload this presentation by Lucia also on our social media. So if you want to see it again, please just follow us and reach us on YouTube channel. Okay. Thank you again. Thanks a lot, Lucia.
Thank you.
See you.
Bye.
Next month. Bye bye.
Ciao. Grazie. Spero si sia capito.
Sì, sì, sì.